So this talk is going to be a little bit of an overview and tutorial on this new family of sequence models called structured state space models. Some of you may have heard of a model released last week called Mamba, and this talk will sort of build up through the history of these models up until this most recent version, which is kind of the culmination of this line of work. So many of the exciting applications we've seen of modern machine learning and deep learning have been driven by what I call deep sequence models, which are just deep neural networks that operate on sequences. And these can be used for all sorts of modalities, from things like text, such as the GPT family of models, to audio, video, time series, and even domains that aren't actually normally viewed as sequences, such as images. So they're very powerful and flexible and have been driving a lot of the progress in our field. And so we're going to talk about kind of a new core layer, a new type of core sequence model, the state space model. Before we get there, let me define more narrowly what I mean by sequence model. So my definition is just going to be a black box transformation that maps one sequence to another sequence. So this slide illustrates just a one-dimensional input that gets mapped to a one-dimensional output of the same shape. And this is kind of the simplest case, but it's also characteristic of this whole family of models. And in deep learning, we normally have extra channel dimensions and a mini-batch dimension. And so pretty much what I mean by sequence model is this black box interface that maps tensors of this shape to each other. And some of the most, many well-known families of models kind of fall under this interface, including more classically the recurrent neural networks and convolutional neural networks. And more recently, we've seen things like NeurODEs and, of course, attention. And these all fit this interface. And so what I mean by deep sequence model is when one of these things gets incorporated into a deep neural network by combining with other components such as normalization layers, linear layers, residual connections, and so on. And usually these blocks get repeated really deeply. And I think that the architecture is pretty orthogonal to what's to the core sequence model layer, which is this black box again. And so the difference to me between, say, a resonant and a transformer, of course, the architectures have a bunch of small differences, but really it's what's at the heart of it. A CNN is characterized by convolution, transformer is characterized by the attention. And so I'll be talking about the new family of this core sequence mixing layer, the state space model. And when you incorporate this into a deep neural network, you get a deep SSM or a state space neural network. And you can do this in many ways. But what's at the heart is this black box layer. So there's going to be a couple flavors of these that I'll talk about. And to be more precise, I call these structured state space models for a reason that I'll define later. And so I'll go through the two main flavors of these. One is going to be the basic structured SSM, also known as S4 models. And then I'll talk about variations of these that led to the new Mamba model. Before going on, let me give an illustrative example of the type of task that we're going to be talking about most, which is autoregressive modeling, such as for modeling language. So for these models, they're a generative model where you generate sequences one step at a time and feed it back into the model. And at first glance, this seems a little bit different than the simple sequence mapping interface because there's this generation in the loop. But the point I want to make is that when training these models, you still adhere to this black box sequence-to-sequence mapping. And at training time, what happens is that you're conditioning on every single time step at once, and for every time step, you're using the context to predict the next token. And so during training time, basically, you just plug in this black box sequence mapping. So I won't get into all the details, but this is going to be kind of the illustrative example that we care about the most. Okay, and let me talk a little bit about kind of the most common families of models that adhere to this, these sequence models. So classically, before transformers, recurrent neural networks, or RNNs, were the most popular family of model for this. These basically take in inputs one step at a time and operate on them and then produce an output one step at a time. They're a very natural causal model and have good inductive bias for sequences. But the downside is that because they're sequential, they're slow to train on modern accelerators like GPUs, and people ran into a lot of issues on the optimization front, such as vanishing gradients. And but all of these, the strengths and weaknesses are basically characterized by the sequential nature of this model. On the other hand, attention, which is the most ubiquitous sequence model used these days, is characterized by having dense interactions. And this, again, leads to its trade-offs. So it performs really well because you can kind of look at every single pairwise interaction at once. You can skip over the past context, and it's very parallelizable on GPUs. But the downside is that because you're looking at every pairwise interaction, it scales quadratically in the sequence length. It's slow at inference time, which also scales with the sequence length. And this is a big problem that people have worked on for many years. And so we're going to be trying to get the best of both worlds here. And so the new selective state space model that we'll build up to is an attempt, a big step, I think, toward getting the strengths of all of these models without the drawbacks. So it's going to be very efficient. It's going to scale linearly in the length of the sequence. You can do autoregressive inference fast. The performance is really strong. I think it's the first model that's going to match transformers on some really difficult data like language. And when you have both of these things, you can get lots of other capabilities, such as improved ability to handle long context, which requires both very efficient models and models that can model the data well. Okay, so that was kind of the overview of sequence models. And the next sections, I'm going to talk about the two flavors in more detail. So first, let's talk about the original flavor of structured state space models. Now, these are kind of inspired by a very classical type of model. These are more classical state space models, which were first introduced by the Kalman filter many years ago, and which is still in use today. And so these are kind of based on continuous time systems, and it's basically just a very simple linear differential equation defined by these two equations. Oops, sorry. Now, when used in deep learning, this is what are called structured state space models. And these are loosely inspired by these classical SSMs and have a bunch of things in common, but actually are more related to modern deep sequence models such as RNNs and CNNs. And it turns out that they have a lot of really nice properties and ways to work with them, which we'll go through in a little more detail now. So first of all, let's define this through our definition of a sequence model. Again, a sequence model maps a sequence to a sequence. And so we're just going to view, when we apply a state space model in this way, I sometimes call it a state space sequence model to differentiate. But actually, it doesn't natively operate on sequences. It was defined through this differential equation that operates on functions. And so the way to think about this is that it's a parameterized set of equations that maps a one-dimensional function to a one-dimensional function. And how does it do this mapping? So here are the equations again. Basically, at the bottom here, we have this input x of t, one-dimensional function, and it's going to output this one-dimensional output y that goes through this latent state h. And that's where the name comes from. There's a latent state that controls the dynamics of this model. And so in more detail, the first equation here is a linear differential equation that blows up the input from one dimension to n dimensions, where n is a controllable hyperparameter, and think of it as on the order of, say, 100. And how does it do that? So you take the input, you hit it with this column vector b, which blows up the dimension to, say, 100. And then it goes through this simple linear differential equation governed by this square transition matrix A. And this is a deterministic differential equation, and so there's a unique output here, h, which is the hidden state. And then the second equation is just going to project this back down to one dimension again through this row vector c. So these two equations, very simply, just the first one maps the input to a hidden state. The second one maps the hidden state back to an output, and the whole thing is linear in the inputs. And it's basically as simple as you can get in terms of a differential equation. So that's mechanically how they operate. And in terms of the properties, because these were kind of loosely based on these continuous time systems, they are a kind of unique family of model that has connections to continuous time signals, and that gives them some certain benefits. For example, it has really strong inductive bias for continuous signal data, such as audio, as opposed to language. And you can do really interesting things like zero-shot resolution change and other benefits like that. And so we see some of the unique properties already. Now the next two properties are how they relate to, so this one is just how it relates to classical continuous time SSMs. The next two properties are about how these structured SSMs relate to RNNs and CNNs, and particularly different ways of computing the model. And so the first one is, so I've defined an equation, but I haven't said how to actually compute it, right? And the most naive way to compute it is just by literally unrolling the differential equation. And so you can view this as saying that I have this input x, and I'm trying to compute the output y. And I'm just gonna read in my inputs one at a time, feed it into this differential equation. And you have to do a little bit of extra machinery, such as this discretization step, which I'll skip, but it's pretty simple. And then it basically turns into a linear recurrence that you can unroll. And so at every step you get one new input and you generate one new output. And this is basically just like an RNN. This way of computing the model has strengths and weaknesses. The main strength is that it is a natural recurrent model, and so this is going to be really fast and efficient in the right setting. And so in particular, let's say we're actually seeing the data in an online setting, one at a time. And say we see one new data point and we want to compute one new output. Then this output is actually, if you view this as a mathematical function, it's a function of the entire history of the input. Every single previous data point is contributing to this output. And so with most sequence models, you might expect this to scale with the entire length of the context you've seen so far. But with recurrent models such as SSMs, you can compute every new output in constant time. And so this is a major difference, computational benefit of these models over normal sequence models such as attention. And so this is the second property, which is one way of computing the model, which is probably the most straightforward way. You just do it recurrently, and it has these benefits in autoregressive or online settings. Now the downside of this is that it can be slow if you actually, so for example, during training, you actually see all the inputs ahead of time. You see your entire input sequence, and you don't need to feed it in one at a time. And if you're still feeding it one at a time, then your model is going to be slow for the same reasons that RNNs were slow to train, because they're sequential, and this is not going to be parallelizable. And so one of the main bottlenecks of getting these sort of recurrent models to actually scale and be effective is overcoming this. And this led to the furthest flavor of SSMs. It turns out that there is a way to bypass all of this. Let me also mention that besides the sequentialness, there's another issue with these SSMs in general, which is that I mentioned that you are mapping this one-dimensional input and output, but it goes through a state that is much larger, say 100 times larger. And then what happens is that if you were trying to compute this naively, then even materializing the state itself is going to be a major bottleneck in your computation memory requirements. And this was actually the biggest issue with some of the early work in this space. And so, and I'm mentioning this because the fact that you have a larger hidden state is important, and it's going to come back later. But you have to find a way to compute this larger state without paying the efficiency costs. And so one way of doing this is this final representation of the SSMs, which is that they're equivalent to convolutions, and there's a way of computing the map from the input to the output in one pass that bypasses the hidden state in the middle entirely. The reason you can do this is because this flavor of state space model is equivalent to a single convolution. And so computationally what this looks like is that we're going to have we have these parameters A, B, C, and D. Actually, only A, B, C matter for this. Those parameters uniquely define a specific convolution kernel or filter, which is illustrated in green here. And so we first compute that filter, and then it turns out that the entire output of the entire model, Y, is just a straight up convolution of your input X with this convolution filter K. And so you can compute all of this in a single pass, parallel over the whole sequence, using well-known techniques based on the fast Fourier transform. And so yeah, so you can get away with, during training time, you can get around the computational issues. And it turns out this is actually very fast in practice to compute. And I think also this gives a lot of intuition into the nature of these models. And I think the simplest way to think about them is that instead of being related to, say, RNNs, they're actually in some ways quite different from the classical type of RNNs like LSTMs, GRUs, and they're much more closely related to CNNs. And so like including both so for example, the fact that the core layer here is just a linear transformation that can be represented as a convolution, and then the neural network architectures are also going to be more closely related to CNNs. So this I think helps with the intuition of how to think about these models. The main difference is that the convolution kernel is parameterized implicitly instead of storing every single element of the kernel. And so this convolution kernel is not, you're not learning it directly, but it is a transformation of these other latent parameters A, B, and C. And because of that, there's also differences such as this convolution kernel is infinitely long, and this also is related to the long context abilities of some of these models. And so that's the final main representation here, which is the convolution one, which gives these models the parallelizability. And so again, just to recap these three representations, these SSMs are based on this continuous time differential equation, which gives them strong inductive bias for certain types of data. And they can be computed in either of two different ways in practice, either as a recurrence, which is very good for online or autoregressive settings, or as a convolution, which is very good for training time. And so a typical use case of this, using both of these views, is that we would train the model in convolution form during training, which is very fast, and then switch it into the recurrent mode for generation. And because these are both computing the same thing, it's pretty cool that you can kind of switch back and forth between these representations. So let me emphasize kind of some of the main characteristics of this flavor of SSM, which will be the ones that differ from some of the later flavors like Mamba. So first of all, these models are what are called linear time invariant, which just says that the parameters are invariant through time. So in particular, these ABC parameters, they're basically constant matrices that are learned but are fixed through every time step. And there has been many flavors of models that are built on top of this that kind of keep to this linear time invariant constraint, and that's because this is what gives the model the ability to switch between these views. To have both this recurrent and convolutional view, your model has to be time invariant. And then there's many types of models that can build on top of these, and a lot of them perform pretty similarly because, and so basically any of these models that are time invariant are going to be pretty similar in practice. Now the second thing that I want to focus on is that these models have this characteristic of the state expansion property. By the way, I only just realized my mouse is in the middle, sorry. So I mentioned that the model, so this is kind of going back to the old control loop diagram where you have this one-dimensional input X, one-dimensional output Y, and this higher dimensional hidden state that's undergoing this feedback loop through the recurrent dynamics. And this is a higher dimensional state, and one of the things that we had to focus on was that we can't materialize it because it would be too slow. And the linear time invariance was the most important technique for letting us bypass this hidden state. Yeah, and so both of these, we're gonna need to, so these are really good for like the continuous type problems, but to work well on discrete problems, we're gonna need to revisit this. So that's why I'm bringing these up. One more thing that I wanted to mention briefly is that the term state space model is a little bit overloaded. So let me just really briefly clarify some of the nuances between flavors of these. So these did originate kind of with this particular form of this equation from the Kalman filter. But really a state space model is anything with a state space. And this is a really broad concept. Pretty much anything can be a state space. And pretty much every field has its own flavor of these. So originally in controls, we have these Kalman filters. In other fields like reinforcement learning or robotics, basically any process that involves state transitions such as MDPs or and so on. There's many other related concepts in robotics as well. These are all other forms of state space models. Computational neuroscience has its own version. And in more classical machine learning, these SSMs are actually synonymous with things like hidden Markov models or other types of probabilistic models, which are very different than the flavor of model that I just described, which is completely deterministic and kind of operates in continuous time, whereas some of these older SSMs operated in discrete time and were probabilistic. And deep learning, people have used this to refer to even any RNN or even any autoregressive model. Even a transformer can be called a state space model, which I'll elaborate why in a second. And so this term is a little bit overloaded, and to really clarify the difference, as I mentioned, the type of the model with these properties that I just described, I actually call state space sequence models because they adhere to my definition of a sequence model, this sequence-to-sequence map. And actually it turns out that you have to put a little bit extra into them. You have to make these models structured in a certain way in order to be actually really efficient in practice. And so in practice, all these models have a certain type of structure that, that leads to this original name of S4, or the structured state space sequence model. And so I'm just mentioning this because I think it's become, these SSMs have really come to the limelight. But like when you're using them in this deep learning context, they really refer more narrowly to this flavor. Whereas, and to keep in mind that like there's many other types of SSMs that other people work on. Yeah, and also I personally don't know a lot about a lot of these, so don't ask me about Bayesian SSMs. So, okay, yeah, so kind of the summary of these types of models are that these are linear time invariant models based on this differential equation. They have multiple properties and ways of computing them. And they also have this property of state expansion, which is going to be very important, but that makes them very slow to compute, and you have to find ways around it. So this computational issue is kind of very core to working with these types of models. Okay, so next let me talk about kind of how to overcome some of the issues with them, which led to this new, very recent flavor of SSM called the selective SSM. So the main intuition behind this is that I claim that we can understand the trade-offs of sequence models a lot better by thinking about what is their autoregressive state. What do I mean by this? So you can think of any autoregressive model as a state space model. And the state of a model is just what the model is remembering in between time steps. So any sort of generative model that's operating sequentially, you can think of as a state space model. And then we just have to think about what is it remembering? What is the nature of its state? So let me illustrate this through the main families of sequence models that we've talked about. And so at the very beginning, I mentioned RNNs and transformers. And I said that RNNs were characterized as being sequential, but transformers are characterized by having these dense pairwise interactions. Now I'm going to rewrite this and say that actually it's a better, there's another way to characterize these, which is a little more illustrative. And I claim that RNNs are characterized by having a fixed size state. So here the state is illustrated in blue. This little blue rectangle in between the cells is a fixed size vector. That is what the model is passing in between time steps. So when it sees another input, it updates its fixed size state using this input, and then it uses its state to generate the output, but it's always going to have this fixed size state in between time steps, right? And the same trade-offs that we talked about before are also consequences of this characterization. They're efficient because they have this fixed size state that leads them to have constant time generation and linear time training. But this is also why they didn't perform as well on some challenging information-dense tasks such as language modeling. Because if you really have that much information, these models are being forced to compress them into a small state, and it just can't remember and synthesize information properly. And on the other side of the spectrum is the transformer, or more accurately, the attention mechanism. And here I claim that these are characterized not by having dense interactions, but by having a state that is a cache of the entire history of the model. So if you're familiar with transformer inference at all, you may have heard this term called the KV cache, and that's that's literally the state of this model. So basically, at every single time step, let's say you're operating on one more input, and you're getting a new query, then basically this new input is going to kind of attend over the entire cache of your history, every past key and value, right? And so that is the model state, and that's why a single new step takes linear time scaling with the sequence length. And that, in turn, is why during training time you have quadratic time over the sequence length, because every single element is linear over the entire past. And so this characterization of attention as being a stateful model where the state is just a cache of the entire history gives it both the strong performance, the modeling performance, because the model is caching its whole history, so it can kind of skip over any past. It can kind of model all these, every possible interaction, but it's also why it's slow. And so I think this view is very powerful, and it's kind of what motivates a lot of my work on state space models. And just to summarize again, the trade-offs here are that attention is explicitly doing no compression of its past, and that makes it perform very well, but not be very efficient. And on the other hand, recurrent models such as the classical RNNs as well as SSMs have a very strong state compression because you're compressing it into a fixed size state. And this makes them much more efficient, but also can make it hard to model information dense data. So what we want is really to get the best of both worlds. And how do we get this? So you can kind of view this, come at this from either direction. For example, starting from attention, the point is that caching the entire history is wasteful and honestly doesn't make sense. What if there's just a lot of garbage in your history? What if there's filler tokens and so on? And so really what you want your model to be doing is compressing its state to only remember what's relevant in its past. And from a recurrent point of view, the issue is not about compression, but about getting more expressive. You need the state to be expressive enough to be capturing all the right information in the context. And so first of all, it has to be large enough to be able to have the memory capacity for all of that. And that's one issue with past RNNs. And second of all, you need a more sophisticated state update function that's able to let your state learn what it needs to when it sees new inputs. And so this was kind of one of the main issues with the time invariant ones. And to overcome it, it's really simple. All you need to do is make your original time invariant parameters, instead of being learnable parameters, you make them functions of the input. And so this gives them a lot of added expressivity into the state update function. So in particular, basically the A, B, C, and optionally D parameters, we're just going to make them linear transformations of the input. And this very simple change makes a very big difference on some types of data. So we call this the selection mechanism because what this allows the model to do is selectively remember what it needs to remember from the past. And there's a lot of interesting synthetic tasks that you can show that this makes a huge difference. And it's very nice because it's just one simple change. But actually, it's not quite that simple because there was a reason why we couldn't do this before. And actually, I came from an RNN background and I was trying to make this work for many years actually. But there was a lot of other efficiency challenges. So in particular, I had kind of been emphasizing that one of the reasons that the classical form of structured SSMs had to be linear time invariant because you have to do that to be efficient. And in particular, you need to bypass materializing this larger hidden state. And by the way, one reason why I kept mentioning that we need that state expansion is because of this whole compression aspect. This is one of the issues with past RNNs that they don't have a big state, and so they have trouble learning stuff. But here we can get a hidden state of the size, say 100 times bigger than what was previously used. The issue is, again, that you just can't materialize that larger state. And so one way of overcoming it is using convolutions, but then you're forced to be time invariant, and you don't get this expressive state update. So here we have to get a little bit more into the implementation details and figure out how to do this. The implementation is going to be particular to the type of accelerator you're using. And so here, to get around to overcome the efficiency issues, we basically have to leverage the idea that we have to accept the fact that we do have to materialize the state, but we just have to do it more carefully in the right level of the GPU memory hierarchy. And so we're not going to materialize it directly in main memory or HBM, but instead you transfer the weights into more efficient shared memory or SRAM, materialize the state there, do all the computation there, contract it back down to one dimension, and then read it back out. And so this gets really into the hardware-aware aspect of the implementation. And otherwise, this would be too slow. So you kind of need both of these things. You need first the selection mechanism, and then you need a fast algorithm to compute it. And again, there's only one real difference between this and the older form. The only difference is that some of the SSM parameters, instead of being learnable parameters, they are now projections of the input. So there's going to be some associated shape changes in the tensors. And then finally, because of this change, we can no longer, it's no longer time invariant. We can no longer compute with a convolution, and we have to do it with a particular algorithm that we call the selective scan. Yeah. So in summary, basically, the idea behind these, this flavor of selective state space model is all about the state representation, and that's at the heart of all of these models. We can see intuitively that a smaller state is going to be more efficient, while a larger state is more powerful. And so we just want to compress the state into the minimal representation that's necessary to learn whatever you need to model in the data. We saw that the previous linear time invariant forms of SSMs have very poor compression, but they're efficient, but they are not compressing the context well. And we see that attention is doing no compression at all. And the selection mechanism is basically the idea to achieve this best of both worlds, where you can compress the data selectively into just what the model wants to learn. In particular, it allows you to focus or ignore inputs across the sequence length. And then finally, we also need to, we need this state expansion to get this is a controllable hyperparameter that lets us create a state that's exactly the size that we need, depending on the data and the task. And you have to be careful about how you implement this in order to not pay significant efficiency issues. Okay, so let me say a little bit about some experiments now. I purposely kept this very short, actually, because there's been lots and lots of works around these models, and they've achieved really strong results in all sorts of modalities. I'll kind of focus on just the more recent ones. So first of all, one thing I do want to say is that I think of data as being on a spectrum, where data like text is really discrete, and there's other related forms of data like graphs and, say, DNA that can kind of be viewed as types of language, and they're also very discrete. And on the other hand, lots of other types of data are generated from real continuous time processes, such as audio and video, as well as many forms of time series. And these data I think of as more continuous. And the inductive bias does matter. So there's no free lunch here. And having models that work well on different types of data, you do need to change the model a little bit. So in particular, for example, the first part of this talk on the linear time invariant flavors of models, such as S4 and many derivatives, these work really well on continuous data, things like modeling raw audio and so on. And they all perform pretty similarly on these types of data, I think. On the other hand, they don't work as well on data like text, and that's where this flavor of selective SSMs shines. So this is where Mamba excels, and as well as there's been many other concurrent works kind of in the same flavor, such as other papers came up with similar ideas at the same time, such as this one called hierarchical gated recurrent networks. And these are kind of the first versions of these RNNs that really work well on data such as text. And these are actually more specialized for text as well. So basically, Mamba might not work as well on data such as raw audio, and you have to switch back to the linear time invariant formulations. So I think that the most promising results that these newer flavors of models have achieved are basically on text, though, because the old ones were not able to do this. And here I have some scaling laws that we did with a bunch of related models. So we basically scaled these models from pretty small model size up to over 1 billion parameters, closely following the chinchilla scaling law protocols. And we did this on multiple sequence lengths. So here I'm going to show it a little more on the longer sequence length of 8,000. And so what we started from was the classical transformer, and we basically adhered to the GPT-3 training recipe as closely as possible. And so this is the baseline that most people compare against when they do these scaling laws. And that's, I think it's a yellow line near the top. And then there's been lots and lots of works recently on doing these subquadratic models. And here are a few of them that actually tried to scale up on language to a larger size. So these include the H3 model, the hyena model, the RWKV, which is a type of RNN that's actually also very closely related to SSMs, as well as RetNet, or the retentive network, which is another, actually all four of these models are very closely related. And all of them, they all perform pretty well. And many of them are, in fact, better than the original style of GPT-3 transformer. But what we did was we really tried to train the strongest possible transformer baseline. And so what we call the transformer plus plus here was our attempt at basically using whatever has been published, the most modern recipes, most modern architecture, and trying to make the strongest possible model. I actually think that our baseline is probably stronger than Llama 2 here. So we really spent a lot of time trying to make this model really good. And this is much better than the original transformer and better than all these other variants. And what's exciting is that Mamba is actually matching this transformer at least flop for flop. So on the x-axis, we're doing scaling laws in terms of flops. And I think Mamba, it's fair to say that it is the first attention-free model to really be competitive with the strongest possible modern transformer. And I think there is a bit of subtlety here. So this is comparing against flops on the x-axis. So one of the reasons why it is better is because it is doing a lot, especially as your sequence length gets long, it is performing fewer calculations because of the linear scaling in sequence length. So you can actually see that for the same model size and the same sequence length, it might be doing a little bit worse, but it's also doing a lot less computation. So there are some subtleties here. And then we also took our pre-trained models and trained them out to a pretty standard recipe on the pile and compared against all of the comparable models in open source that were trained on the same data set. And what we saw was that Mamba matches, or it beats all the models of the same size on every single evaluation. And at least compared to these models, it was often as good as a model twice its size. To be transparent though, I think that the baselines here are a bit older and not the most strong baselines. And these were the only ones we could compare against at these model sizes and train on the same data that we did. But I think that realistically, Mamba is about as strong as a very strong, like if you take the strongest transformer at any given size, I think Mamba's not going to be like twice as good. It's going to be about the same strength. But even that's very exciting because people have been tuning these transformers for years, and now we actually have a different type of model that seems like it's going to be competitive, and I think this will open up a lot of science questions that we can start answering. So these architectures also are not just, they don't just work on text. And on other types of data, we kind of just drop and replaced Mamba into other types of pre-training pipelines and also found similarly very good results. So as an example, people have been looking into training foundation models on DNA, which is another modality that looks a lot like language, just with a different vocabulary. And we did a similar type of scaling law and found that Mamba scales much better than the baselines that have been trained in the space before. And we use the same kind of similar transformer plus plus recipe. Here, everything is much less tuned. So we just have an apples to apples comparison with something reasonable and found that Mamba just worked better out of the box in these modalities. And if you really compare the performance versus model size, we're actually, both the transformer and Mamba scale really well, but Mamba is actually seems to be matching it with much fewer parameters. And finally, because of its efficiency and ability to selectively synthesize data in the past, it also scales really well with sequence length. So one thing we tried is basically making the sequences longer and longer during pre-training while controlling for the batch size and the amount of computation. So every single data point here is exact same amount of computation. And we found that Mamba actually just seems to strictly improve the longer your context gets. And again, this is very interesting, I think, which is not true of a lot of the previous models because they lack the selection mechanism. And similarly, on downstream tasks, we also find that the longer the context, the better the model is doing. So hopefully this opens up some applications in other modalities that you really need long context. Yeah, so these are just kind of like two different modalities that we looked at, but we've looked at all sorts of other things. We've looked at audio. I know some people have been looking at this for video and images, and been reporting that it seems to work really well across the board. So pretty exciting. Finally, let me just mention the efficiency aspect again, more quantitatively. So here we kind of just scaled the sequence length up and compared a bunch of different primitives, including attention, the fastest version of attention that exists right now, as well as other types of sequence modeling primitives such as convolutions or this recurrence, also known as a scan. And we do find that the hardware-aware implementation speeds up over a naive implementation of the recurrence by a factor of, I think, around 30 times. And as the sequence length gets longer, you're getting like orders of magnitude faster than even the fastest version of quadratic attention, which is as expected. And the last part about the efficiency is that what happens if you switch this to recurrent mode during generation time. Because of the fact that we have this compressed state, we don't have a KV cache, these models are also much faster during generation time, which is one of the main benefits and one of the main motivations for working on this. So compared to a transformer of around the same size and around the same amount of optimization in the generation loop, we're getting generation throughputs of about 5 times faster. And so, yeah, this is, I think, a really exciting time to be looking at these alternate architectures. I think there's lots of questions that are not answered and that we don't understand. There's lots of downstream capabilities that would be interesting to look into, like, do you need this big state or not to do things like in context learning downstream? Can you prompt and fine-tune these models the same way? These are all things that I think we're only just starting to look at, and there's a lot of interesting progress ahead. Yeah, that's the end. So do we have time for questions?
We thank the speaker. And we have time for questions, so please come to the mic if you have any.
Hi, super nice talk, thanks. So in previous versions of state space models, there was a real emphasis also on capturing long-term dependencies, particularly with the Hippo framework. Do you find that that's still important to get these kinds of results?
Yeah, so I think that there's a lot of theory in the first versions of them for capturing long-term dependencies, and I think they were more on in very specific regimes, or like it's related to the nature of the data itself. So actually, so I think that those things are really good for certain types of data where you actually have like continuous signals that are highly compressible and kind of can be decomposed into these polynomials or other sorts of bases. And then adhering to that very strict theory actually does help a lot. And so so this relates to the no free lunch that I was talking about. On some types of data, like on audio, for example, if you're doing raw audio or maybe raw video, that theory actually still does help. But it is not, that sort of theory is not useful for compressing different types of data. You can't really, it doesn't really make sense to do a polynomial decomposition of a sequence of text, for example. It's too discrete, right? And so, yeah, so that's kind of the trade-off there.
Thanks.
Thank you very much for this interesting talk. My first question is, if you actually need as much data as transformers, because transformers can be a bit data hungry in other domains as well. So do you need the same amount of data in order to get these types of results?
I think so. So we kind of just started, we basically took whatever transformers do and kind of just match the recipe as close as possible. Actually, I think that kind of benefits the baselines more. And it's very encouraging that we're getting really good results while, playing in their field. But I think that there are really interesting questions to investigate. Like, I think it could change. For example, we did scaling laws based on the Chinchilla protocol, which was meant for transformers, and maybe the scaling laws for these models actually do look differently. These are questions that we just don't know right now, and so I'm just starting to explore these. But I would say, as my prior, data is almost like a separate part of the. It's like an orthogonal consideration, and all of these models probably do need a lot of data still to learn well.
Okay, thank you. And a quick second question: do you think there's a big difference between the previous state space models and Mamba in terms of like video data?
So I think it depends on the nature of the data again. So if you're running these things kind of on the raw data level, pixels or voxels or whatever, then your data is like pretty continuous, and you probably actually do want to use the older flavor. But say you might want to use those in the codec. So you might have some layer that's interfacing with the raw data and kind of compressing it into quantizing it or whatever. You might want to use the older flavors of S4 models there. But if you then have compressed the data into higher level, more discrete, abstract representations, then you probably want to use Mamba, which would probably actually be pretty good for this type of data.
Okay, thank you very much.
I was wondering whether the hardware-aware SRAM materialization was something unique to Mamba or something that would be more broadly applicable to any recurrence type model, and whether you could sort of highlight the difference between this method of time selectivity versus classical methods.
Yeah, absolutely. It should apply to recurrence in general. I mean, these are kind of very classical hardware implementation techniques that should apply more broadly. There is a little bit more subtlety with the particular way that Mamba is defined, so that it's not just computing the recurrence, but also you can parallelize that recurrence over the sequence length because of the fact that the recurrence is so simple. So if you take something like an LSTM or GRU, you could, I think, get a state expansion, and if you're clever enough, you can materialize that only in SRAM. But the recurrence is also going to be a lot more complicated, and there's going to be other issues there, and you can only do it sequentially still. So there's a bit of subtlety there, but yeah, these are more general techniques.
Thanks.
Thank you for the great talk. I have a question about the context extension of recurrent models. It's like we know recurrent models are known for the almost infinity context length, but currently, as you reported in the Mamba, the context extension capability is not infinity. I just wonder whether it's possible to achieve this infinity context given fixed dimension of hidden state and the parameters. Thank you.
Yeah, this is a great question. So I think it is important to emphasize that you're not really getting a free win. Like, we're not claiming that you can really get infinite context with the finite size state because that's just clearly impossible. And so we kind of think of the state as being, you make it as big as necessary for what you're trying to model. So if you are trying to model really, really long context, then you have to kind of think about how much information is there in my context and set the size of your state appropriately. And if you really want to model long-range dependencies that are really also like dense, and you have to, let me give an example. So in the paper, we had another experiment that did super long-range stuff, but in kind of a synthetic setting where you only have to remember like one or a finite number of tokens. And in that case, you can get away with a finite size state because the state is tailored to what information you need to remember. But if you are doing something like language or something where you have really long context, but also actually need to remember lots and lots of stuff in there, then you do have to increase your state size to match. So it's just, again, all about how much information is in your context. And you're not going to have a free lunch by with a finite size state and like trying to model infinite history. In practice, we did notice that if we do language modeling on longer context, then increasing the state size helps more. Whereas on shorter context, increasing the state size doesn't help as much, probably just because we've already saturated how much information we need in the state for that particular task.
So is it true that basically we maybe need to scale up the sequence length and the hidden dimension at the same time if we are training a large model? Yeah,
I think so. So yeah, it really depends on your data and your task. But in general, if you are trying to capture if you're trying to capture more information, then yes, you need a bigger state.